Okay, so line integral. For the introduction, line integral. The line integral is a single integral over a curve in 3D space that can be interpreted as the area under a curve C. An important application of line integrals is the computation of the work done as a variable forces move along an arbitrary path. The idea of line integral involves integrate over a curve, involves scalar field or vector fields, solve problem involving fluids, flow, forces, electricity and magnetism. Okay, so here we have a diagram for example for the curve C. Okay. So next, in mathematics, a line integral is an integral where the function to be integrated is evaluated along a curve. The term path integral, curve linear and curve linear integral are also used. Contour integral is used as well, although that is typically reserved for line integral in the complex plane. So we have work energy that involve line integral, then conservation energy too that involve line integral. So the next one, if a force F is continually applied to an object that moves over a piecewise smooth curve, then the work done by F is the line integral of F over C. So we have work and formula, then we have integral for curve, and then force. Okay, so we have term, let H in bracket xyz equal to term of vector xyz for I, then xyz for j, lastly xyz for k. Be a vector field that is continuous on a smooth curve. So this is the term we have to write in vector field. Okay, so the next one, the line integral of h over c is the number. Then we put some integral for curve h and r. So we have integral respect to a to b, and then we have r prime dot product with h r. Okay, so the next one, let H be a vector field that is continuous on a smooth curve C. The line integral, so we have this formula, same like the above. Okay, is the left in the variant by every direction, preserving change of parameter. Okay, so next we have piecewise smooth curve. So for piecewise smooth curve, we have diagram. So this is example diagram. So we have curve 1, curve 2 and curve 3. Okay, so it will become like this formula. For total integral curve equal to integral curve 1 plus integral curve 2 and etc. Okay, so we have done for vector. Then the lastly, line integral for arc length. Suppose that f is a scalar field continuous on a piecewise smooth curve. So we have vector. Then if SU is the length of the curve from the tip of RA to the tip of RU, then as you have seen, we have this formula in magnitude. Okay, the last one, the line integral of f over c with respect to length s is defined by setting. So we have formula for curve. After that, it will become this formula. Okay, that's all for me.
Okay, Assalamualaikum. I'm gonna explain example 1. First evaluate the equation over the line flow P 222 and Q is 311. For the solution, first compute PQ, which is OQ minus OP. You get 1 minus 1 minus 1. Then use it and define some vector and its first derivative. You get 2 plus t, 2 minus t, 2 minus t. For 0, t bigger than 0 or equal then less than 1 or equal to 1, and you get the differentiate of R. You get 1 minus 1 minus 1. Thus differentiate as respect to t, you get square root 3. From the RT, you get 2 plus t, 2 minus t, 2 minus t where t greater than 0 or equal to 0 and less than 1 or equal to 1. Then hence perform line integral, which is you get the equation. You get this, substitute the 2 plus t and 2 minus t into x, y, z, and square root 3 dt is replaced to ds you get from here. After that, you just simplify the equation and you get this. After you get you simplify the equation, you can integrate. After you integrate, you get this. Then substitute 1 into every t and 0 for the lower limit and upper limit. After you substitute, you get the answer, which is 25.403.
Okay, the next one is example 2. So this is the question. Okay, first for the solution we define RT. After we define RT, we need to derivative RT and we get this answer. Okay, the third one is we find ds. ds, we use this formula r prime t and then we get 5. Okay, next, the last one, we need to substitution and find the area. Okay, we substitute. Okay, and then we get the answer.
Next is application of line integral in engineering field. Line integral play a crucial role in various engineering applications, particularly in the field of electromagnetic, fluid mechanics, and structural analysis. So this is the derivation formula for electromagnetic and fluid mechanics. Line integral has several applications. A line integral is used to calculate the surface area in the three-dimensional plane. Some of the applications of line integral in the vector calculus are as follows. Used in Ampere's law to compute the magnetic field around a conductor. In Faraday's law of magnetic induction, a line integral helps to determine the voltage generated in a loop, calculate the work done by a force on a moving object in a vector field, and calculate work done by a fluid force. Example 1. Calculate the work done by fluid force. Calculate the flow rate of the fluid through a circular path C defined by x squared plus y squared equal to 4. So to solve this question, we can use the line integral of velocity field V along the curve. So the derivation formula is Q equal to integration of closed path V dot product with dr. In this case, the velocity field V is equal to 2x negative y. The path C is defined circled by x squared plus y squared equal to 4. So from that we can parameterize using polar coordinate, which is x equal to 2 cos theta and y equal to 2 sin theta. Then the differential part is given by dr equal to dx dy, when dx equal to negative 2 sin theta and dy is 2 cos theta. Next, we substitute this expression into the line integral formula. Then we get the answer is 0. So the answer is accepted and makes sense because there is no net flow through the closed path. Next, example 2. Compute the magnetic field around a conductor. Considering a long straight conductor carrying a steady current I equal to 10 ampere, use Ampere's law to determine the magnetic field B at a distance R equal to 0.05 meter from the conductor. A. Set up the line integral expression for Ampere's law considering a circular path of radius r centered on the conductor. B. Evaluate the line integral to find the expression for B on term of I, R and any necessary constant. C. Calculate the numerical value of B using the given parameters. Right, so solution for A. The line integral expression for Ampere's law is given by integration of closed path B dot dl equal to mu naught I. Then considering a closed path of radius r centered on the conductor, the path become B dot 2 pi r equal to mu naught I. So from that equation we can get the B, which is B equal to mu naught I over 2 pi r. C, then we substitute the given value, then we get the answer is 4 times 10 power of negative 5 Tesla. So the magnetic field at the distance of 0.05 meter from the conductor is approximately 4 times 0 power of negative 5 Tesla.
That's all from us. Thank you, Doctor.
Bye-bye.